Nari Labs, the team behind the open speech model DIA, published how they serve Qwen 3 TTS, and the headline number is a latency one. Sub-50 millisecond, P95 time to first audio, held through 10 requests per second, on a single H100. They open-sourced both the implementation and the benchmark. What makes it worth an episode isn't a faster kernel, it's a scheduling argument. Here it is, straight from the source. Here is the scope. Their implementation of Qwen 3 TTS 1.7 billion CustomVoice, running on one H100 SXM, holds P95 time to first audio under 50 milliseconds, all the way to 10 requests per second, and stays under 100 milliseconds even at 20. Playback stays real-time throughout. They picked this model because it's one of the most popular text-to-speech models with a permissive license. Before the numbers mean anything, they define the problem, and the definition is the useful part. 4 things have to hold at once. Time from request to the first audible sample must be low. Once playback starts, the client must never run out of buffered audio. Both of those must survive rising load. And the speech has to stay intelligible. Note the word audible. Silence that arrives quickly is not audio that arrived quickly. They ran 4 existing engines at their upstream defaults, 1 request per second, changing only what compatibility demanded. VLLM Omni came in at 278 milliseconds and underran on every single request, which means playback stuttered every time. SG Lang Omni and MStar both sat above a second. Voxserve managed 315 milliseconds cleanly. Nothing is near 50 milliseconds untuned, which is the fair starting point for the comparison. Then they tuned each engine, and 2 changes did most of the work. The first PCMA model returns can carry tens of milliseconds of silence before any sustained sound, so they detect speech onset from short RMS windows and trim it, worth about 80 milliseconds, while making inference no faster at all. The second is how many codec frames you accumulate before decoding. A small first chunk starts playback sooner, larger later chunks keep it fed. Tuned, Voxserve reached 49.3 milliseconds at 1 request per second. And here's why the story doesn't end there. Push the tuned engines to around 6 requests per second, and every one of them is back at 100 milliseconds P95 or worse. Voxserve, the best at low load, goes from 49 milliseconds to 363. VLLM Omni roughly doubles. Configuration buys you a fast single request. It does not buy you a fast 10th concurrent request, and that is the actual serving problem. To see their fix, you need the architecture. Qwen 3 TTS is 3 models doing hierarchical, multi-codebook generation. The talker predicts the first codebook token for each audio frame. The code predictor generates the remaining 15 codebook tokens. And a causal codec turns those tokens into actual waveform samples. 3 stages, 3 different compute profiles, 3 different batching behaviors. Most implementations run the first 2 together and the codec separately. Their move is to expose all 3 as independently schedulable tasks on one shared scheduling surface, an idea they credit to the MStar paper. Now the scheduler can decide whether to run the talker, advance the code predictor, or rush a codec job that's approaching its playback deadline. And note the counterintuitive bit. Fusing the talker and code predictor looks more efficient because it removes a boundary, but it creates a long, non-preemptible unit of work that blocks more urgent jobs. Smaller units give the scheduler more room. The scheduling policy comes from a real observation about speech. Streaming has 2 different kinds of urgency. Before the first chunk of audio arrives, every millisecond lands directly on time to first audio. Once playback has begun, the next chunk only needs to arrive before the current audio finishes. Producing it earlier is invisible to the listener. So requests without first audio get high priority, and established streams only become urgent as their deadline approaches. Running each urgent request alone would destroy batching, so an urgent request is chosen as an anchor, and the rest of the batch is filled with compatible work. The speed number has a cost number attached. At 10 requests per second, their system produces roughly 630 characters of speech per second. Multiply by 3600, and that's about 2.27 million characters an hour. An H100 SXM instance at $4.29 an hour. Therefore, works out near $1.90 per million characters at full utilization, Their comparison points are Cartesia Sonic 3.5 at $49 and 11 Labs V3 at $100. Read that gap carefully though. So, sub-50 millisecond P95, time to first audio, through 10 requests per second, on a single H100, with the implementation and benchmark open sourced, so the claim can be checked. The lesson underneath is that the win came from treating 3 model stages as one scheduling problem with playback deadlines, not from making any one stage faster. And on the cost line, their own footnote is the honest caveat. That number excludes networking, idle capacity, and operational overhead, and assumes a GPU running flat out. Your utilization is the variable that decides whether the arithmetic holds. AI. Explained simply. Subscribe to BirenAI so you don't miss the next one.